Multi-protocol label switching, the concepts. Well, this used to be a completely separate course in the Cisco world where you would go a full week talking about MPLS technology because it was really a niche designed for service providers. As a matter of fact, the MPLS exam, the certification exam that they have, only applied to the CCIP, which was designed to be a service provider level certification that Cisco created. Not so anymore. MPLS has begun to bleed its way into the enterprise from the service providers and become a very viable WAN connection style that overlays our existing WAN types. So what we're going to do as we walk through this video is talk about the concepts of MPLS. And I'm not going to break it down line item by line item here because overall the goal of this video is simple. By the time you're done, you will have a good foundation of what MPLS technology is all about. Before we get into the new technology of MPLS, you have to have that foundation of how a Cisco router processes packets. This will help you understand the benefits of MPLS. When routers first emerged many moons ago, they all did something called process switching. Now, process switching is hardly ever used today at all because it's so very slow. It's a process that the router uses to look up where the packet's going and send it on its way. So let's say this computer on the left-hand side is trying to speak to the computer on the right-hand side. All these packets are going through, and we'll just say packet 3 right here jumps into the router. Now what's going to happen is the router receives it, looks inside, and says, okay, I see some data, I see the protocol, TCP, UDP, the port information, source and destination IP address, source and destination MAC address. So the router receives all that and says, okay, where are you going? Let me look, because I'm a router, at the destination IP address. It looks and says, oh, okay, well, comparing that to my routing table, it looks like you go out this interface. Or maybe you go out this interface to the next hop IP address, because there's another router along the way, not pictured here, but a next hop IP address before you actually reach your destination. So what the router will do is look it up in the routing table, see what the next hop IP address is. Now, if this is the first time it's actually gone to that next hop IP address, before it can really move any further, it has to do something called a recursive lookup, which means send an ARP packet out saying, hey, who is this next hop IP address? And if it's this PC, it's going to respond to that ARP and say, why, yes, here is my MAC address. That's me. And it looks up that information. Once it gets it, the router strips off the old MAC addresses, meaning the source and destination right here, and puts on the new MAC addresses, being the source and destination right here, and forwards the packet along its way. Next packet comes in, same exact thing happens. It looks it up in the routing table, says, oh, okay, I think I know where you're going. You're going out this interface or this next hop IP address. Now, the good news is since it already sent the ARP out, it has an ARP cache and knows how to get to that. So we don't have to do the ARP, but looks it all up in the routing table, strips off the MAC address, and you know the rest of the story. That's the story of process switching. Very inefficient, very slow. So Cisco developed this thing that they called fast switching. And so what a lot of routers used by default, probably until 2003, 2004 timeframe, was when everything really started switching over to Ceph, which we'll talk about in a moment. Fast switching, what it did was said, you know what? Chances are that if that computer's sending one packet to that computer, it's probably going to send others. I mean, if you think about it, think about like voice over IP. When you're talking on an IP phone, it's sending about 50 to 60 packets every single second that you're speaking into that phone. So in typical computer communication, just thousands of these things are being sent across the network. So what happens is the very first packet that's sent, let me get some of these arrows that's off here. The very first packet that's sent, which is maybe that one, goes through the process switching process where it's looked up in the routing table, reverse ARP, trying to, or not reverse ARP, but reverse lookup to try and figure out the MAC address, tie those things together and send it on its way. But once that first packet goes through that process, that information for these two computers is moved into the router's cache. Meaning from then on out, when this computer wants to speak to that computer, it is stored in memory and it just looks and says, oh, are you next in sequence? Oh, you are? Go ahead. Next in sequence? You are? Go ahead. You know, it just keeps forwarding on through. It doesn't have to look at the routing table. It doesn't really have to make any more decisions. So it increases in speed drastically from using process switching for every single packet. Now, fast switching was somewhat limited because since that information was cached, sometimes if you put on an access list, it would goof it up and it would revert back to process switching. And fast switching definitely didn't support things like per packet load sharing, where it could say, okay, this packet goes that way, this packet goes that way, back and forth, because that, you know, that would require multiple cache entries. It can't handle that. It wasn't designed to do that. And that is why Cisco came out with that final one called Cisco Express Forwarding, otherwise known as Ceph. What Ceph does is well, Cisco says the feature it eliminates is the first packet problem, meaning that you do have fast switching and it's great, but you still have that first packet lookup. And if you've got a lot of hosts, hundreds or thousands of hosts going through this router, I mean, it's going to be a significant load and a significant slowdown. So what Ceph does is pre-build the cache. Rather than just waiting for the first packet to come in, before it even starts sending packets, it will actually create a separate table from the routing table, and some of you may have heard of this before, called the Forwarding Information Base, or FIB, that is loaded into memory. This fib is essentially a replacement for the routing table. Once the fib is created, and that's done on boot up, the router no longer looks at its routing table because it moves everything into a memory cache. Now the fib says where every network is and how to get to the next hop IP address, but likewise, Ceph takes another step, and once the fib is generated, it also generates an adjacency table, which pre-maps. Let me just write this down here. Adjacency table. It pre-maps all of the next hop IP addresses and the next hop MAC addresses, or whatever layer 2 information is there. So essentially you have these giant tables already cached in memory saying if we get something from this network, send it to that next hop, and right next to it is the adjacency table that says that next hop is that MAC address. So there is no packet 1 problem. Likewise, Ceph adds the features of per packet load sharing without the slowdown that we had with the process switching by reverting back from fast switching to process switching. So Ceph is what we use nowadays on just about all our routers. What's the drawback? Well, it eats up more memory because it essentially takes the routing table, generates a forwarding information base, which is primarily, I'm trying to think of a good way to put it. The forwarding information base is like taking the routing table down to almost a layer 2 sort of thing, meaning it can go almost as fast as a switch when it's going through, because everything's already cached in memory. All the lookups are already done. So the forwarding information base does eat up extra memory along with that adjacency table that it creates. And that's why if you have a huge routing table, Ceph can be a problem. Cisco has come out with extra cards that they call VIP cards that you can add in those high-end routers that have hundreds of thousands of routes going through, where it kind of offloads Ceph to a different card where it's got more memory and can hold all that stuff. So that's how routers forward packets in modern times. Now, what's the problem? Why do we need yet another way of forwarding packets like MPLS? Well, Ceph. Let's think about it. Define it out, spell it. Cisco Express Forwarding. Now, one word in there tells you that that is a mechanism that will only work on Cisco routers. Give you a couple seconds. What do you think it is? You got it. Cisco. It says Cisco Express Forwarding. So what that does is lock that in as a Cisco proprietary forwarding method. What about the other routers? What if you wanted Ceph-style speed going through a service provider network, which maybe has some other non-Cisco routers? I don't know why you would, but other non-Cisco routers sitting in their cloud somewhere. Ceph's not going to happen. It's going to slow down. That's where MPLS steps up to the plate. I like to call multi-protocol label switching, or MPLS, Ceph for the rest of the industry. It allows people to have the extremely fast layer 2 style forwarding on non-Cisco equipment and pass that extreme speed style forwarding to other routers. It essentially allows you to affix a label at layer 2 of the packet. And you can see this little label here. It's actually, I was reading a magazine article, and for whatever reason, I was thinking when I created this slide, I thought, you know, I need a label. Let's put a picture of a label on there. And then it jumped in my head that Siemens, I don't know if you've ever heard of that company, Siemens. I was reading an article about them in one of the mini magazines that I read. And they have come out with that label. That's actually a picture of it right there. It is a label that is an LCD style screen. It's paper thin, and guess how much it costs to make it? A couple pennies. Guess what's going to happen with that label? That is poised in 5 years or less. That's what the article said anyway. To replace all labels on like products in the store. When you're going through and you see like UPC labels on like a bag of chips and stuff, it'll have one of these instead. And it's an LCD screen. It's like having a monitor as a label. And the store will be able to, for instance, there's a sale on chips. They go, boop, type it in, and that little label, you know, adjust the price on all the chips, so now the chips have the right sticker on there showing the correct price. And since it's an LCD screen, it can actually be fed intelligent information that allows you to have, like, you know, a little guy on there doing a commercial on the back. I kid you not. That's where that little label is going. I can't even imagine where it's going to go for like computer monitors and stuff like that. You're going to have paper thin computer monitors that you just kind of stick on the screen and then roll up and put it in your bag when you're ready to go. That's a 30-inch monitor. Anyway. I don't know why. I just had to tell you guys about that. I just read that and I thought it was really interesting. But anyway, that's what MPLS does. It sticks a layer 2 label inside of the packet header that really just associates it with all sorts of stuff. That label can correspond with what destination network that packet is going towards. It could correspond to what level of quality of service it gets. It could correspond just to an outgoing interface. Maybe you don't know the next hop address. It's just labeled 39 says, oh, send it out your Ethernet 0 interface. And it could have other layer 2 info. For example, you could have a label correspond to a frame relay DELC. The sky's the limit. And I know right now you're probably looking and going, huh? It's kind of vague. You know, why are we adding these labels that have this stuff? Well, what it does is it moves everything down to a layer 2 method where everything can be stored in memory. For example, when you have an MPLS router, and I'm telling you, lots more. You know what? I'm gonna hold that explanation because I even have a slide that's dedicated just to explaining how MPLS is used for forwarding. But this label is like a little chip programmable label. It can correspond to all kinds of stuff inside of the packet. So let me give you a 10,000-foot view of how packet forwarding looks in MPLS, and we'll dig deeper as we get further into the topic. This is our scenario. We have a client over on the left-hand side that just has a Class A network, 12.0.0.0/8, and the cloud represents their service provider. Now, this client over on the left-hand side will play a part, but as of right now, they're just somebody, we'll say they're just somebody connected to this service provider that gets internet access. So the clients don't usually support MPLS. Not usually. Some of them do, but primarily it's a service provider technology. So they'll be advertising in the 12 network via BGP, or it could be a static route on the service provider redistributed into their network and so on. So that route will be received by the service provider, 12.0.0.0, and sent to all these other routers via, most likely, iBGP or maybe ISIS, some kind of service provider routing protocol, to where all of the routers now know about the 12 network. That is normal routing. That's building a routing table, and everybody says, okay, this is the next hop IP address. We've got it all figured out. Life is good. But now we take an extra step. These are all MPLS-enabled routers. The actual term for them is LSRs. Label switch routers. So we've got all these connections going through the cloud, and they all take that network in their routing table, and every single one of them assigns a label to it. Now, this label is just a number. It doesn't really mean anything. It's arbitrary. As long as the one router doesn't have two exact same labels, it's okay. They could even come up with duplicate labels in this cloud, as long as we don't have the same label on a single router, you know, like 228s or something like that. And they make sure that doesn't happen. They just dynamically allocate it. So they all just say, okay, I'm going to say 28, 32, and 50 for my label. Now, here's the next step. A second advertisement is sent. This one comes up and says, hey, I assigned the 12 network 28. This one goes down and says, I assigned it 50. And then this one jumps back up and says, oh, well, I assigned it, oh, whoops, got that wrong, didn't I? This one says, I assigned it 32. And then this one down here assigns it 50, but it comes back and says, oh, by the way, I assigned that 50. Now, all these routers are actually going to build what's known as a lib. And again, we'll talk all about the terms later, which says, okay, we've got the 12 network, and the top router assigned it 32, you know, and that's, you know, we're talking about the top router, so that's my local label. The bottom router on the right assigned it 28. They actually write down all the labels that were assigned to all their peers. So they keep track of all their peers' assignments for that label. They then build a second table, which I call the action table. I won't get into the exact terms yet, but it tells routers when they receive a label what to do with it. For example, this router might say, well, if I receive a packet labeled 32, I'm going to send that to my peer router down in the lower right-hand corner, and I'm going to stick the label 28 on it. So I know right now it's looking a little fuzzy. Here's how a packet would come. So this router comes in and says, hey, I've got a packet destined for 12.5.1.9. This router gets it, looks in its routing table, because it's not a label, it's just a normal routed packet. It says, oh, so you're trying to get to the 12 network. That's what my routing table says. It looks at its label table and says, oh, well, I need to forward that to this top router. We'll say router C right here at top. And it says, so I need to stick label 32 on there, because that's what router C recognizes as the 12 network. Router C receives label 32 and just looks at its action table. It doesn't even look at the network anymore. It's not concerned that it's going to 12.5.1.9. It just sees a label coming in, layer 2 information, saying, oh, you are label 32. It looks at its action table and says, oh, well, label 32, that's not for me. That needs to go to label 28. So all it does is rip off that label 32, stick on 28, and send it down here to, we'll call this guy router A. Okay. Router A receives the label 28, looks at it and says, oh, well, that's a local label. I don't have any other label actions defined for that, so I'll tear off my label. And I'll send it out just as a normal IP routed packet. So when this router gets it, it never sees a label at all. MPLS is that seamless that clients don't actually realize what happens. It's kind of like VLANs, if you think about that. You know, for a corporate network, the PCs have no idea what VLAN they're all on. It's just a switch technology behind the scenes. That's the same thing with MPLS. Let's now dig a little bit deeper. How does the technical aspect of this work behind the scenes? I mean, it's all pretty, just labels flying every which way. But, I mean, what's really happening? First off, you have a router that's running MPLS that really divides itself into two planes of existence, the control plane and the data plane. The control plane is where all of the routing is happening. You may remember back to like your CCNA days and the discussions there where you learn the difference between routing protocols and routed protocols, the difference between something like OSPF and TCP/IP. Well, the control plane is essentially the routing protocols for IP, that's a layer 3 routing protocol to really build the routing table on a router. And also you have a routing protocol where you exchange MPLS labels. We'll learn in just a little bit. It's actually known as the label distribution protocol, which is all its goal is to send labels every which way and tell all the routers what labels that each other is using. That's all done using the control plane. Control, as the name implies, kind of sets up the control for the network. It sets up the framework for how things are going to be forwarded. The data plane is where the action occurs. That's known as the forwarding plane. That's another name for it. And that's where it sends data based on layer 3 or layer 2 information. MPLS is an added feature to a router that allows it to go much faster than typical routing protocols would. It allows all of the forwarding to happen down at layer 2. So essentially, if you boil it down, your router becomes like a switch, almost as fast as a switch can go, because all it's looking at is layer 2 information. But MPLS is just a feature. So I want to make sure I emphasize that if a router receives a packet and there's no label on it, it's going to be a router. It's going to look at the layer 3 information and say, oh, you're going to 5.2.1.1. My routing table says go this way. And we go back to our fast switching or our Ceph methods where we're really just going with typical routing. Data plane is the plane that also takes care of label swapping. Label swapping is kind of the action that occurs, and I compare it to almost like stripping MAC addresses. As labels come in, they'll have like an incoming label, and the router looks at that incoming label and says, oh, you're supposed to go down there. Something has to take that incoming label off and put an outgoing label on there, so when the downstream router receives it, it goes, oh, that's my label, and I know what to do with that now. That's part of the function of the data plane. It's the action plane, taking off and putting on new labels. If you were to grab a packet sniffer and start capturing MPLS frames as they cross the network, you wouldn't have to dig deep into that packet to find the MPLS labels. The labels squeeze right in between the layer 3 information, the IP address information, and the MAC address. Now, looking at this packet, this is the data. This is like the protocol, TCP, UDP, port numbers, that kind of thing. IP header, source, and destination, and then right in there goes the MPLS label, right behind whatever layer 2 infrastructure you're using. In this case, I show the MAC address because I'm assuming this is frames running across an Ethernet network. This is something that demonstrates the power of MPLS. It can operate no matter what layer 2 infrastructure you have. So you could run an MPLS network over your local area network environment. You could run it between routers on a LAN. You could run it between routers crossing a PPP connection on a point-to-point T1 lines, or frame relay, or ATM. The point is, it doesn't matter. MPLS goes right behind that header, so the labels are going to be processed as layer kind of 2.5, if you will. The layer 2 is the medium that gets you there. The label is sitting right behind it. This makes MPLS totally independent of whatever layer 1 and layer 2 technology and transport you're using, which is what the manufacturer intended. And if you were to look inside of this label, you would find a 32-bit value where the first 20 bits right here are dedicated to the label itself. That, if you plug it into a scientific calculator, will give you somewhere around 1 million some values, 1,100,000 something values that you can have for the label. The point is, we're not going to run out of labels anytime soon. Label values 0 through 15 are reserved though. So you can use anything other than 0 through 15, and your router is going to dynamically allocate those label values. So most of the time, you don't even care. We'll talk about what some of the reserve values are a little bit later. Next to that are some experimental bits, is what they're technically called. Bits 20 through 22, that's 3 total bits that you have for experimental purposes. Now, I'm not talking about assigning a lab rat an MPLS label. I'm talking about it's left up to a vendor what they want to use those bits for. I can tell you Cisco uses the experimental bits for quality of service markings. Just so happens that if you get into quality of service, you have class of service, which is switch-based quality of service, and then you have type of service, TOS, which is router-based or layer 3 quality of service markings, and this one gives you the same number of bits that each of those do, 3 bits, which give you 8 total values that you can mark for quality of service. Now, right next to that is the BS bit. I know some of you are thinking, I knew someday we would have a packet that had a BS bit. It does not mean what you think it means. The BS bit means bottom of stack. Sometimes you'll see it written as just the S bit, I'm sure, to avoid the reference. But what this is just one bit. It's either a 0 or a 1, and it tells whether or not this is the last label in the stack. Your frames, your packets can have more than one label. This is just one. Like you can see this zooming right back down here. This is a packet that has 3 labels. Each one of those labels might have some different meaning. One might mean what kind of VPN you're crossing, or what kind of quality of service marking you're using, whereas another one matches directly to the network. The BS bit tells you if you are either a 0, meaning I am not the last label in the stack, or a 1 being the last label. In this packet down here, label 3, right before the IP, would have the BS bit of 1. That's a funny bit. From there, TTL, time to live, does exactly the same thing that the TTL field does in the IP header. It's just that since MPLS really takes the place of IP-based routing, it needs some kind of mechanism to stop loops. Like, what if a packet just gets sent and it's unreachable, but the routers are looping? You don't want this immortal packet that never dies. It's the same kind of thing where it can deduct TTL values as it passes through routers, eventually saying, okay, you've reached the max, now you're dead. Now let's officially hit the terminology of MPLS, item by item, so that you can have a full grasp of the terms that you use when you speak about this technology. First off is the label switch router and the edge label switch router. The label switch router is from the RFC standard. It is considered a router that does nothing but MPLS. I guess you could call this a core router because it's kind of sitting in the middle of everything, just doing MPLS, receiving labels, sending labels. It can do IP, but its primary purpose is to switch labels, sending and receiving. Cisco came up with their own term for this because they actually got into the MPLS game before it had become an RFC standard. Cisco will call those provider routers, or you'll see them abbreviated as P routers, things that are submersed in the provider, not actually speaking to customers. Now in the RFC standard, they also have this term, which is Edge LSR, and these are the ones that are still in the provider network, but that are typically stripping labels as it sends it out to the customer. Since MPLS was primarily designed to be a service provider technology, the customer routers shouldn't receive a label, and if they did, they would probably drop the frame. So the Edge LSR is usually the one that's adding labels as it goes into the core network, into the ISP, and stripping labels as it comes out. Cisco has their own term for it. They call it the Provider Edge Router, or PE router. Now, control plane and data plane we already talked about. To hit the high points again, control plane is where we have all the routing information being forwarded, both for routing protocols and the label protocol to send those out. The data plane is what's actually doing the forwarding, the one that's actually adding and removing labels, changing header information as it goes out. Now you can see the official routing protocol of MPLS. It is known as the Label Distribution Protocol. When they developed MPLS, they had a big decision to make. They were either going to tweak one of the existing protocols, like OSPF or something, to also carry label information with it, or they would come up with a new protocol just for label information. And what they decided was, we want a new protocol because it's too hard to tweak an existing one. And that's what the Label Distribution Protocol is just a protocol dedicated to sending labels everywhere. Now we come to what I would say are the 3 most important things to understand about MPLS. The forwarding information base, which we talked about way early on in this video, and we talked about label information base and the label forwarding information base. But now we'll actually see what they are, and then we'll see some practical examples to apply them. The forwarding information base, just like we talked about when I discussed Cisco's Ceph technology, Cisco Express Forwarding, the concept is to move the routing table into a complete cache structure where it just shows the network and the next hop to get there. Well, the forwarding information base is the same thing as it always is. It's just with MPLS implemented, the forwarding information base may show a network with the next label to get there instead of the next hop IP address. Now, the label information base is a base or of a table, I should say, on the router that holds nothing but labels matched to a network. For example, a label information base, to use that previous example, might have the 12 network, 12.0.0.0, and it'll say, okay, I have a label of 28. That's a local label. But 12.0.0 on router C has a label of 52. And 12.0.0.0 on router D has a label of 69. And all these different labels come out and jump into place. Now, that label information base is used whenever something is going to take a different direction and go, okay, I'm going to go to router C. Oh, what label do I need? Let's check the label information base. That is built from the label distribution protocol. Finally, you have the label forwarding information base. You kind of combine the two together, the fib and the lib, and you have lfib. The label forwarding information base is the action state. It's going to say, if you receive this label, then go ahead and forward it to this router and tag it with that label. It really is the action table of MPLS saying what labels should go what direction, so that when a router receives packets, it knows where to send them. So let's take those terms and put them to action, and I think you'll gather more meaning of what they are used for. You can see the MPLS process. It's pretty simple. 4 steps. Number 1, the routers will build their routing table via whatever routing protocol or static routing system you have in place. Second, the MPLS enable routers will put labels on each route. So let's say, okay, I've got the 12 network, you get this label. The 13 network, you get that label, and so on. Those are considered the local labels. They will then advertise their labels to other LSRs, to other routers that are enabled for MPLS so that they can receive them. Now, I know we talked about the edge LSRs and the LSRs. Everything is considered an LSR if it's running MPLS. So don't think that, oh, just the core ones are getting it. We're talking all the MPLS capable routers will get those and receive labels from everything else. Finally, all the LSRs will build their forwarding information base, the label information base, and the label forwarding information base. Those 3 tables I just mentioned at the very end. And that's going to be what I'm talking about in these next few examples as we see packet forwarding in action. But I want you to catch, before we do that, that MPLS is almost like running a second protocol on top of everything. Are you getting that feeling? As I've been talking about this, it's almost like, yeah, you've got your normal routing protocols. RIP is sending routes as it always does. But now we have this extra routing protocol that's sending labels everywhere. And what we've effectively done, I just want to emphasize the efficiency before we look at the how, is we've effectively moved routing down to a layer 2 label process, making the routers almost as efficient as a switch when they're sending their data. Let's take those steps now and watch the process of MPLS happen using a live network scenario here. Up in the top, I have a client, and again, it's running the 12 network, 12.0.0.0, and it advertises it into the service provider, which we'll say is this little triangle right here of routers, and the network is advertised in, we'll say via BGP. Now this router receives that 12 network and says, okay, well, since you sent it to me, you are the next hop address. And you can see this top box right here is the route table. That's what we've always known it as. Now that route will be propagated to all the other routers in this service provider network using whatever internal routing protocol the service provider uses. So everybody now knows about that network. Now, the second thing that happens here is all the routers, once they know about that network, you remember the second step here is they will say, I want to assign that network a label. Now I'm just showing one of them right here. I have this router, 12.0.0.0. It's considered a local route. That's a big part of the label information base you can see on the right. And I will assign it label 85. So this router now knows its own local label. This router down here will do the same thing, and it will assign it its own label. This router over on the right-hand side will assign it its own label. Let's say this one assigns it 6785, and this one assigns it 78 in the upper right-hand corner. Everybody's got their own local label now for that network. Has forwarding changed? No. If this router sends a packet destined for the 12 network at this point, or this client sends ones in and it has to go across, this one will send it untagged, unlabeled, over here to the router. We'll call it router A over on the left-hand side. Router A will not use labels at all either because it only knows about its own local label. So in the label forward information base, in the actual forward information base, we haven't replaced anything with labels yet. Everybody's just generated a local label, but they're not being used because they haven't been advertised. Aha. Now we come to the next step. Everybody will send each other their label using LDP. So label 85 will be sent over to routers. We'll call them B and C over here on the right-hand side. They'll send their labels all around, and labels will be sent everywhere to the point where routers A, B, and C now know what everybody has assigned to network 12. This is what the label information bases will look like once all of the routers had distributed their own local label information base. Now my router labels disappeared, but we'll again say this is router A over on the left-hand side. Its label information base says, aha, 12 network, that's my own local network, and I assigned it label 85. And I heard from 15.1.1.1 that they assigned the 12 network 6785, and that happens to be this neighbor down here. We'll call them router B. And I heard from 15.2.2.1, that's router C over on the left-hand side, that they assigned network 12 label 78. Now, same thing over here. You can see just glancing at all of these different label information bases, they've all tracked what local label they've assigned and what all the other partners, all the peers in this network have assigned. Now, I do want you to know that MPLS is a peering system where peers will exchange their labels. It's not going to be one of those things where everybody in the entire MPLS world knows what labels everybody else has, because they're only concerned with the next hop address. Where do I send this next? From this information, the routers will generate their label forward information base, which is their action steps. And this, I think, will put a lot together for you. Router B, let's look at his label forward information base. You can see that we have, if I receive a label, a packet destined with the label 6785, I am to replace that label with 85 and send it out serial 0. And we'll assume that this port right here is serial 0. So router B, whenever it receives a label, let's say this link is down right here. Router C is going this direction. It's going to send a label, and it's going to say, hey, my label information base said that you have the 12 network tagged as 6785. So I'll go ahead and send the packet tagged with 6785 to you. This one gets it and says, oh, 6785, that goes to label 85, and I send it out this one. This is all being done at layer 2. And now you can see why this label information base, label forward information base, LFIB, is the action table. It tells all the routers what to do. Now I just have one entry in the label forward information base, but there will typically be many, such as backup routes. I don't have any backup routes for label or router C or B. You can see router C's label forward information base says if you receive a label for labeled 78, which is for the 12 network, that's my local label, go ahead and replace that with 85 and send it out serial 1, which is maybe directly connected over here to router A. So they will swap labels. This is the action table where labels will be swapped to get there. Now, router A's label forward information base just says if you get label 85, perform the pop action. Now, you'll hear that term a lot with popping a label. It sounds like popping a pill. Popping a label means yank it. You're done. You've reached the end of the trail. And now look at the layer 3 information. No longer do we look at the label. 85 is gone. Router A now looks and says, oh, you're going to 12.9. Okay, you're going to go next hop IP address 10.1.1. And no labels are ever sent out to the client down here. The client is label-less. So they're just going to receive the layer 3 information that they're used to. Now, the creators of MPLS decided that even that process was a little efficient. So what they introduced was something known as PHP, as we begin to overlap acronyms with the developer world and PHP coding languages. PHP in the MPLS process stands for penultimate hop processing. What it means is that why do we need to send it to router A just for it to look at its label forwarding information base and pop it anyway? When router A sends it out, it's going to tell everybody, hey, I'm 85 and I'm the end of the trail here. And everybody else will realize, oh, okay, label 85 is the end. So if they see that one of these things is going to label 85, they will automatically pop the label before they send it to router A. What that does is it actually eliminates router A's two lookups, because now instead of receiving a labeled packet, looking at the label forwarding information base and going, oh, I need to pop this, popping it off, and then saying, okay, what IP address are you? Oh, you're going to 10.1.1 is the next hop. Okay, I gotcha, and sending it that way. Two lookups happen. Instead of doing it that way, router B and router C see that and go, oh, well, since label 85 is the end, before I send it out my serial interface, I'll go ahead and pop the label. So when it gets to router A, it doesn't have to look at its label forward information base. It just looks at its fib, its normal routing table, and says, oh, you're going to this next hop address because you are received right here. So MPLS makes itself even more efficient when you introduce that concept of PHP. So that's the scoop on the concepts behind this new technology, multi-protocol label switching. So to hit the high points of what we talked about, because we talked about a whole lot of stuff. First off, the standard routing methods, process switching, fast switching, and Ceph, and the difference between those two. Something that Cisco's had around for quite some time, but has never been an industry standard, which is Ceph, makes things much faster. We then defined MPLS as essentially an industry standard way to get Ceph on every single router, and maybe even a little faster, because we're now moving everything down to a layer 2 label rather than using a layer 3 routing table. We then looked at how routers keep track of MPLS, how they exchange information, and how they really understand what labels go to what. And we looked at some of the concepts behind MPLS there, and introduced MPLS architecture of how you can squeeze in an MPLS header in just about any kind of frame. It just goes in front of the existing layer 2 marking. Finally, we looked at MPLS terminology, kind of the dictionary of MPLS, and walked through an example of how MPLS routers processing packets, really demonstrating the difference between the fib, the lib, and the lfib, what those three tables are used for.